All right, let's talk about something that could be a huge deal for food safety. We're going to break down a brand new technology that could pretty much stop food poisoning in its tracks. I'm talking about a faster, smarter way to find salmonella before it finds you.
So, you're at the grocery store, you pick up a package of chicken, and you just have to wonder, right? How clean is this, really? I mean, sure, we all do our part. We wash our hands, we cook it till it's done. But what if the problem is already there, long before it even makes it to our kitchen? How can we really be sure it's safe?
Yeah, and the reason we have to ask that question is often because of this little troublemaker, Salmonella. It's a huge cause of food poisoning all over the world, and you guessed it, poultry is one of its favorite hangouts. See, the tricky part is, the bacteria can just chill in a bird's gut, not making the birds sick at all. But then, during processing, it's super easy for it to get onto the meat we end up buying.
Okay, so the big challenge is pretty obvious. How do you find this stuff? The way we do it now, well, it's reliable, but it's slow. You have to send a sample off to a lab and then you wait, and wait, sometimes for days. And think about that, by the time you get a result back saying, hey, there's salmonella here, that food could already be out in the world, sitting on a store shelf. What we really need is something totally different. Something fast, something portable, something you can use right there on the spot, at the farm or in the processing plant.
And that, my friends, is exactly where our story today begins. Scientists have cooked up something pretty brilliant. It's basically a tiny electronic bacteria trap. Now, the fancy name is an electrochemical aptasensor, but don't worry about that just yet. All you need to know is that it's built to solve this exact problem.
So, what's this thing made of? Let's break it down. It's really just 3 key ingredients. First up, you've got this special base. It's a mix of graphene and protein. Think of that as the high-tech circuit board. Then, you have the most important part, a special DNA trap. This is the real magic. And finally, you just need a little bit of electricity to see what's going on.
Okay, let's zoom in on that DNA trap, because it's so cool. The scientific term is aptamer. Now, this isn't like the DNA inside of you and me. This is a single strand that scientists have designed to fold itself into a very, very specific shape. And that shape is like a custom-made lock that only one key can fit into. And that key? It's a specific molecule on the surface of a Salmonella bacterium. It's a molecular mousetrap, built to snapshot on one thing and one thing only.
All right, so we know the ingredients, but how do you actually build this thing and make it work? Let's get into the process.
Now, this diagram shows the whole process from start to finish. And yeah, I know, it looks a little complicated, but trust me, when you break it down, it's really just a simple, elegant assembly line for a tiny bacteria detector.
Okay, so building this sensor is a super precise 4-step recipe. Step 1, you lay down that special graphene protein base onto an electrode. Step 2, you activate that surface with some chemicals to make it sticky in the right way. Step 3, you attach all those little DNA traps, blanketing the surface. And finally, and this part is absolutely crucial, you block off any empty spots left over. You have to do this, otherwise other random stuff could stick to the sensor and give you a false alarm.
And here's where the real genius of this thing comes in. It's so simple. The whole sensor works on what scientists call a signal-off mechanism. It's kind of like a light switch that's designed to turn itself off when it finds salmonella.
So here's how that light switch works. When you have a clean sample, no salmonella at all those little DNA traps are just sitting there open. You run a tiny electrical current through the sensor and it flows right across the surface, no problem. You get a nice strong electrical signal. That's your all clear. The light is on. But what happens if salmonella is in the sample? Well, the bacteria float by and bam, they get snagged by those DNA traps. Now, a bacterium is pretty big compared to the electrode surface, so when it gets stuck, it acts like a giant roadblock. It physically blocks the path. So now when you try to run that same electrical current through, it can't get through as easily. The signal gets way weaker. It drops right off. And that drop, that's it. That's the alarm bell. The light switch just flipped off and you know you've got salmonella.
Okay, so that's the theory, and it sounds great on paper. But you know what really matters? Does this thing actually work? Well, the researchers put it through its paces to find out for sure.
First question, how good is it at finding really small amounts? The answer is incredible. Seriously, this sensor can detect as few as 3, that's not a typo, 3 bacteria cells in a milliliter of liquid. To put that in perspective, that is an insane level of sensitivity. It's like being able to find 3 specific people in a packed football stadium. Just wow.
Okay, so it's sensitive, but is it specific? Can it pick salmonella out of a lineup with other bacterial bad guys? Just look at this chart. It tells the whole story. See that huge bar on the left? That's the response when Salmonella is there, a massive signal change. Now look at the other bars for things like E. coli and staph. They're practically flat, nothing. It means those little DNA traps are doing their job perfectly. They completely ignore everything that isn't their one specific target. It's a total sharpshooter.
All right, so we've got sensitivity, we've got specificity. But that's all in a nice, clean lab. What happens when you throw it a real curveball? What happens when you try to use it on actual food, which is, a pretty messy and complicated environment?
And this right here is the moment of truth. The researchers took clean chicken samples, and then they deliberately added a known amount of salmonella. Now, don't worry about all the numbers and the scientific notation in the middle. Just look at that last column, the recovery rate. See how it's hovering right around 100%? That means the sensor found pretty much exactly the amount of bacteria that they put in there. It's proof positive. This thing works, and it works incredibly well, even in the real world.
So, when you put all this together, what does it really mean? Let's take a step back and think about the big picture here, because this is why this little sensor is such a big deal.
Look, this thing could be a total game changer for food safety. We're talking about results in minutes instead of days. It's portable, so you can test right at the source, on the farm, in the factory, wherever. It's designed to be cheap to make. And maybe most important of all, because it's so incredibly sensitive, you can catch a contamination problem way, way earlier, stopping bad food from ever even getting close to a store shelf.
And all that leads to one final, really hopeful question to think about. If you can make testing for dangerous bacteria this fast, this cheap, and this easy, so easy that you can do it everywhere, all the time, could technology like this actually make big food poisoning outbreaks a thing of the past? It's a pretty amazing thought, and this research just took us a huge step closer to making it a reality.